You know that old advice people give you when you're starting a new job? Fake it till you make it.
Oh yeah, project confidence, act like you belong, and, eventually you actually figure it out.
Right. And we usually treat that as, good, practical advice for humans. But here's the terrifying part. When it comes to artificial intelligence, faking it is actually the nightmare scenario.
It really is, because in AI, faking it, it has a very specific technical meaning. It means the model is giving you the right answer, but for completely the wrong reason.
It's memorized the test questions.
Exactly. Or maybe it found a loophole in the logic, but it hasn't actually learned the subject.
And that distinction between memorization and actual understanding is, well, it's the defining battle line in AI research right now. Today, we're going deep into the black box. We're looking at a stack of research that tries to answer one single massive question. How do we get a neural network to stop cramming for the exam and actually start thinking?
In the field, we call this the generalization problem.
Right. And to solve it, we have to look at three very different, almost conflicting viewpoints. We've got a massive 20-year survey that suggests the only solution is brute force.
Just scale up.
Then we have a theoretical paper on this weird phenomenon called grokking that suggests the solution is just patience.
And then you have a team from Microsoft claiming they can break all the rules just by writing better textbooks.
It really is a tension between bigger, longer, and smarter.
And the answer might determine whether we get superintelligence or just a really expensive parrot.
So let's start with the problem itself.
Yeah.
We talk about generalization all the time, but in the papers we're looking at today, specifically this survey by Chris Rolls, they argue we're being a bit lazy with that word.
We are. In the industry and in the media, honestly, we tend to treat generalization as, binary. Either the model works or it doesn't.
Smart or dumb.
Smart or dumb. But Rolfs outlines that it's actually a spectrum. Think of it like a ladder.
Okay, walk us through the rungs of this ladder. Because I think most people assume that if an AI can identify a cat, it knows what a cat is.
And that would be the bottom rung. Rolfs calls it sample generalization. This is the easy stuff. Let's say you train a model on photos of golden retrievers from a specific data set.
Cool.
Maybe they're all professional show dogs. Then you test it on photos of golden retrievers from the same data set that it just hasn't seen before.
And it succeeds. It says dog.
Right. But that's barely learning. That's just pattern matching within a very tight box. As you climb the ladder, the difficulty spikes. You get to distribution generalization, where maybe the lighting is different. Then domain generalization, where maybe it's a sketch of a dog instead of a photo. And finally, at the very top, you have scope generalization,
Which is
basically human-level reasoning, applying the concept of dogness to a situation you have never, ever encountered before. But the Rolfs paper points out that most models today fail way before they reach the top.
they don't even get close.
No, they fail as soon as we shift the context even slightly.
And this is where that line in the city experiment comes in. I found this absolutely fascinating because it exposes just how fragile these systems can be.
It's a perfect illustration of the problem. So researchers took a standard computer vision model 1 that had, high accuracy on standard benchmarks. It knew what a lion was.
It had seen thousands of them.
It had seen thousands of lions in its training data.
But think about those photos. Where are lions usually photographed?
The Serengeti, the savanna, yellow grass, dirt, blue sky, maybe a zoo enclosure.
Right. So the researchers did something tricky. They used DALL-E to generate a synthetic image. A lion, looking perfectly normal, distinct features, big mane, but it was walking on a concrete city sidewalk.
Now, to a human, this is instant. It's a lion. It's weird that it's in the city, but the background doesn't change the species of the animal.
Well, of course not.
We understand the object, not just the scene.
But the model.
It fell apart. It failed to recognize the lion 50% of the time.
That is a coin flip. For a state-of-the-art model, that's abysmal.
And it gets worse. When it guessed wrong, it didn't just say, I don't know. It confidently labeled the lion as a Tibetan Mastiff or a Chow Chow.
Because those are big, fluffy, brownish animals that are usually found on sidewalks.
Precisely. This reveals the cheat code the model was using. The model hadn't learned lion equals big cat with a mane and teeth.
Yeah.
It had learned lion equals orange blob surrounded by yellow grass. When you remove the grass, you broke the correlation. It was relying on a confounding variable, the background rather than the feature itself.
That's the faking it part. It's like a student who memorizes that the answer to question 5 is C, but doesn't
Doesn't read the question. Exactly. If you shuffle the questions, they fail.
And the Rolf survey highlights that this isn't just a funny edge case. This is a systemic issue on what they call hard data sets, where the test data is significantly different from the training data. There's consistently a generalization gap of 20% or more.
It's a huge gap.
So we have a gap. The models are cheating. They're addicted to context. The obvious question is, how do we fix it? As a human, my instinct is to say, hey, model, look at the mane. Look at the teeth. Ignore the grass.
You want to teach it the rules.
I want to teach it the rules. We call that feature engineering, right?
Yeah, you, the human, try to hand design the features or the rules to help the machine understand what matters.
But our next source suggests that my instinct is completely wrong.
Worse than wrong. It might be historically doomed.
So this brings us to the bitter lesson. This is a concept from a famous essay by Rich Sutton, and it was the centerpiece of a paper by Yousefi and Collins. They analyzed 20 years of computer vision abstracts.
From 2005 to 2024.
To see what actually works.
Yeah, this was a massive study. They used LLMs to grade these thousands of papers they wanted to see. Did the researchers who tried to be clever, who designed specific features like look for the main win?
Right.
Or did the researchers who just poured more compute into the system win?
And why is the lesson called bitter?
It's bitter because it hurts our ego. It's a pill we don't want to swallow. Sutton argues that we love to think our insights into how the mind works are valuable. We want to build our knowledge into the AI.
We want to feel like we're the architects of its intelligence.
Like proud parents teaching a kid to ride a bike.
Yeah.
Exactly. But the bitter lesson states that historically, the only two things that matter in the long run are learning and search. Basically, massive computation.
So every time we try to build in our own clever rules,
we eventually get beaten by a generic algorithm that just uses more data and more power.
So brute force wins.
Effective brute force. The analysis showed a massive, undeniable trend. In 2005, everything was about handcrafted features. By 2024, those papers had almost vanished, replaced by deep learning and massive scale.
But correlation isn't causation. I mean, just because everyone's doing deep learning doesn't mean it's the only way, right? Maybe it's just a fad.
That's true, but the study also looked at impact. Papers that aligned with the bitter lesson, the ones that prioritize scalability and computation over human design, got significantly more citations. They became the foundation of the field. The industry voted with its attention, and it voted for scale.
So if I'm a researcher and I'm spending months trying to teach my model to understand the concept of gravity or object permanence by writing specific code, I'm wasting my time. I should just buy more GPUs.
According to Sutton and the trends in this paper, yes. The argument is that human intuition is brittle. We don't actually know how we recognize a lion. It's subconscious. So when we try to code ruse for it, we simplify it too much and we mess it up. Computation, on the other hand, is ruthless and consistent. If you give it enough power, it finds patterns we didn't even know existed.
But there was a nuance in that paper regarding search. You mentioned learning and search.
Good catch.
Yeah.
Yeah. Learning is what we see in things like ChatGPT pattern matching on a huge scale. Prediction. Search is what a chess computer does. Planning ahead, looking at future possibilities, traversing a tree of decisions.
Right.
And the study found that while learning skyrocketed, search lagged behind for a while.
Why is that?
It's harder to parallelize. It's computationally expensive in a different way. But the expert note suggests that with the newest generation of models, like the reasoning models we're seeing now, like OpenAI's O1 series, search, is making a comeback.
Okay.
The pendulum is swinging back to models that think and plan before they speak.
Okay, so the bitter lesson tells us to trust the scale, trust the compute. If the model thinks a lion is a dog, don't correct it manually. Just train it bigger, train it harder.
Right, feed the furnace.
But that implies a smooth ride. If I double the compute, I should get double the intelligence, or at least a steady improvement. But our next source throws a wrench in that gear. It turns out the road to intelligence is weird.
It's less of a road and more of a roller coaster. This brings us to the paper by Davies et al. On grokking and double descent.
I love these terms. Grokking comes from that old sci-fi novel, Stranger in a Strange Land, right? It means to understand something so intuitively that it becomes part of you.
Exactly.
Yeah.
And in AI, it refers to this bizarre phenomenon that really confused researchers when they first saw it. Imagine you're training a model. You watch the accuracy on the training data go up to 100%.
Perfect score.
It has memorized every answer in the textbook.
But on the test data, the stuff it hasn't seen?
It's failing, random guessing, zero generalization.
So usually as a data scientist, you'd stop there. You'd say, okay, the model's overfitting, it's just cramming, cut the power, let's try again with different settings.
That's what classical statistics tells you to do. Stop before you overfit. But these researchers found that if you don't stop, if you keep training way past the point of common sense, sometimes for 10 times as long, something magical happens. Suddenly, without warning, the test accuracy shoots up. It goes from 0% to 100% almost vertically.
Wow.
The model groks the problem.
That makes no sense. If it already had 100% on the training data, what was it doing during all that extra time? Just sitting there.
That is the mystery. And to explain it, the paper proposes a theory about pattern competition. They suggest the model isn't just learning one way to solve the problem, it's fighting a battle between different types of circuits in its brain.
So two types of patterns.
Yes. They call them type 1 and type 3 patterns. Think of type 1 as fast heuristics, cheap tricks.
Like orange blob equals lion.
Exactly.
Okay.
Or take the math example they use, modular division. A type 1 pattern might be, if the number ends in 5, the answer's 5. These are easy to find.
Okay.
The model finds these almost instantly. That's why training accuracy spikes early. It found the cheat codes.
But cheat codes don't work on the test data because the new numbers don't follow that specific accident.
Correct. That's why test accuracy stays low. The model is happy because it's acing the training, but it's using a trick. Meanwhile, there is a type 3 pattern. This is the general solution.
The actual logic.
The real mathematical formula.
Yeah.
But that's hard to learn. It takes more connections. It's slow. It requires organizing many different parameters perfectly.
So for a long time, the cheap trick is winning.
It is. It's doing the job on the training data. But, and this is the key, the cheap trick is imperfect. It's messy. The general solution is elegant and efficient.
So the model is slowly, quietly optimizing in the background, even though the score isn't changing.
Yes. It's called weight decay or regularization. The model prefers efficiency. Over thousands of extra steps, the general solution slowly becomes more efficient than the cheap trick.
And eventually.
Eventually, it crosses the threshold, the model abandons the trick, switches to the real logic, and boom, you get generalization.
That's incredible. It's like the model is having an epiphany. It realizes, oh, I don't have to memorize this list. I just have to do division.
It is an epiphany. But notice what this means for the bitter lesson. Sutton said, add more compute. Grokking says, add more time. Both of those are incredibly expensive.
Yeah.
We're talking about burning massive amounts of electricity just waiting for the model to change its mind.
It feels inefficient. We are basically waiting for the model to stop being lazy and doing the bare minimum.
Which leads us to the final question of this deep dive. Do we have to wait? Or can we force the model to learn the type 3 pattern, the real logic, faster? Can we rig the game?
And this is where Microsoft enters the chat with a paper that has a very arrogant title. Textbooks are all you need.
It's a clapback to the famous Attention is All You Need paper that started the whole transformer revolution, but they kind of earned the title.
How so?
This paper challenges the idea that you need massive scale or massive time. They suggest you just need better data.
Set the stage for us. What did they build?
They built a model called Phi-1. Now, in the world of large language models, Phi-1 is a toy. It has 1.3 billion parameters.
And for context, GPT 3.5 is roughly 175 billion. Palm is over 500 billion. So Phi-1 is less than 1% the size of the models it's fighting.
Tiny. Usually a model that small can barely speak coherently. It's like a toddler. But Phi-1 beat models 10 times its size.
On what?
It achieved over 50% accuracy on the human evil coding benchmark.
That's the standard test for how well an AI can write code.
Right. And it beat models that had seen tens of billions more lines of code than it had. It punched way above its weight class.
So how? Did they find a new algorithm? Did they change the math?
No, they changed the curriculum. Most big models are trained on the pile or Common Crawl, basically the entire internet.
Which is full of garbage. Broken code, bad explanations, Reddit arguments, spam.
Exactly. It's noise.
Hmm?
And finding the signal in that noise takes massive compute. The Microsoft team said, what if we don't show it the internet? What if we only show it textbooks?
But there aren't enough textbooks in the world to train an LLM. You need billions of words.
So they made them. They used GPT 3.5 to generate billions of tokens of synthetic textbook quality data. They essentially told GPT 3.5, write a clear, concise tutorial on how to use Python loops, or create a coding exercise that requires logic, not just memory.
They used the big AI to write a lesson plan for the little AI.
And the result was drastic. Because the data was so clean, so dense with actual logic and reasoning, Phi 1 didn't have to waste time learning the type 1 cheap tricks.
Did it get confused by the noise?
It went straight for the logic.
There was one specific example in the paper that really blew my mind.
Yeah.
The pie game example. Can you explain that?
This is the smoking gun for emergent understanding. So they trained Phi 1 on these synthetic Python exercises. The dataset did not contain specific tutorials on how to use the Pygame library or the Teacher library.
Okay.
Those are specific tools for making games and user interfaces.
So technically the model should know how to use them. If it hasn't seen the manual, it should know the commands.
Well, the base model had seen the names of these libraries in its pre-training, but it didn't know how to use them. It would hallucinate methods that didn't exist. But after the textbook, fine-tuning...
Which is just generic coding logic.
Right, which, again, was just generic coding logic. The model suddenly knew how to use Pygame perfectly.
Wait, how? If the textbooks didn't teach Pygame, how did it learn Pygame?
That's the magic. The researchers argue that the textbook data taught the model how to reason about code structure. It improved the model's ability to organize its own latent knowledge.
Right.
It's like, imagine you vaguely know a bunch of French words from watching movies, but you can't speak a sentence. It's just noise in your head.
Right.
Then you take a really good course on universal grammar. Suddenly you can speak French.
You didn't learn new French words. You learned how to structure what you already had.
Exactly. High-quality data reduces the grokking time. You don't need to wait for the model to unlearn the cheap tricks because you never showed it the cheap tricks in the first place.
You gave it the logic directly.
You gave it the logic directly.
That is a powerful concept. It suggests that intelligence isn't just about how much data you have, but how accessible that data is to your reasoning centers.
Precisely. It turns out if you treat the AI like a smart student and give it a good book, it learns faster than if you just throw it into the library and turn off the lights.
So let's pull this all together. We have 3 distinct signals here about the future of AI.
First, the bitter lesson. Scale works. Computation allows models to find patterns humans can't see. Don't bet against the hardware.
Second, grokking. Real understanding takes time. Models naturally gravitate toward lazy shortcuts first, like seeing a lion on the grass. You have to push them, or wait for them, to find the deeper, generalized truths.
And third, textbooks. You can cheat the system. If you curate the data, if you act as a teacher rather than just a data miner, you can get that generalization much faster and with a much smaller model.
It feels like we're moving into a new phase.
Yeah.
For the last decade, the mantra was, big data. Just scrape everything. If it's digital, feed it to the beast.
And now, we are moving to smart data. We're realizing that if we want models that don't think lions are dogs and that understand code rather than just memorizing it, we need to curate the input.
It brings the human back into the loop, doesn't it?
Huh.
The bitter lesson said humans should get out of the way. The textbook approach says, actually, we need humans, or at least human-like reasoning, to design the curriculum.
It does. It suggests that the bottleneck for the next few years might not be how many H100 GPUs you can buy, but how good your synthetic data pipeline is. Can you generate 1 billion tokens of perfect reasoning?
Just if you can.
Because if you can beat the guys with the bigger supercomputer.
That is a hopeful message for anyone who doesn't have $1 billion for a data center. Smart design still matters.
It matters more than ever.
So here's the thought I want to leave you with. We've spent this whole deep dive talking about how AI learns, how it struggles with context, how it needs clear examples, how it needs a good teacher.
Just like us.
Exactly. But if the most effective way to train a superintelligence is to feed it textbooks, clean, logical, curated explanations of the world, what happens if we run out of textbooks? If the internet is becoming flooded with AI-generated noise, are we poisoning the well for the next generation of models?
That is the Ouroboros problem, the snake eating its own tail.
Are we entering an era where truth and clarity become the scarcest, most expensive commodities on Earth simply because they are the only fuel that makes the machines work?
I think we might be. And that makes the job of understanding these sources even more important.
Something to think about the next time you see a lion on a sidewalk. Thanks for diving in with us.
See you next time.